Okay, we're going to measure some customers' parts today using ABTech's MicroForm MFG150 roundness gauge and fitted with an iris centering device which has a mag base. So we'll put the customer's part on that and that holds it, and using the lever to open the iris, and that brings the part into alignment with the rotary air bearing table. And then I will bring the probe over using the slide and the course adjustment, and then as I get close I can dial it in to bring it into the center point up around the 0 there and clear TIR, and it'll tell me how much alignment or misalignment I have. And I am at 2 thou 4/10, almost 2 thou 5/10. Using these knobs on the work table itself, I can translate the table with the part on it so that I can bring that in a little bit better if I desire. The rule of thumb is as long as it's on scale, which is plus or minus 10,000ths of the probe displacement, you don't need to do any better. But for demonstration purposes, I'm just going to show you how easy it is to improve upon the mechanical alignment. So I went from 2.5 thou to 1 thou and 2/10, 1 thou and 3/10, and that's fine. That's good enough. I'm also noteworthy that I am at the focal point of the spherical seat for leveling, and that's where you want to take your centering measurements, and then move down to the extreme on the part and see what the TIR is there. And if you've got a lot of TIR, then down here you would adjust the level and bring that part into alignment. I'm at just under 9/10 for TIR at the bottom, so I'm in good shape. Both are on scale. So now I am ready to move to my next location, which in this case the datum is the ID of the thin wall section, which is the lower part of the ID here. So I'm going to bring the probe up. I'm going to orient the probe so that it's in the ID position, and then I'm going to drop it down inside. And because the datum is on the lower section, I'm going to go all the way down to the bottom, just off of the work table surface, so that I can have my two datum points be as far apart from each other as possible. And now I don't have to look down in there. I can see when my probe touches, it'll start on jump the needle, and then I can use the fine adjust to bring it up. And then I take the revolution, just manually spinning to make sure I'm on scale. I am. So I am going to take a concentricity measurement, and we have two versions, in plane and out of plane. Because I'm taking out of plane, that's the reference axis, and then I'm going to move to a different plane on the part. I select next. There is no reference axis established because I just put the part on there, so it puts me into the reference axis piece and has the instructions right here. So the first thing I need to do, it says, is to put in the height where I am. So based on the scale here, I'm going to put in that it's 2 inches. And I put in what the part name is. I'm going to call this a common spool. That's what the customer defines it as. I'm also going to put in a comment that this is, it's going to already be the datum surface 1, so I'm going to say that it's on the low point of ID. I'm going to toggle between the different locations, that is, and select ID and apply, and now I can use the motor. It's got a DC servo direct drive motor that takes 1 full revolution and orients to the encoder position all the data in the array. There's 8,192 pieces of information synchronized from the encoder with the displacement of the probe that goes into this measurement. So that tells me that I have a roundness of that part of 7/10 89 millionths, and the TIR is 1 thou 148. So, and that's the representation on the polar plot, which I will zoom in so you can see a little bit better. There is a red circle, which hopefully you can make out there. That is the reference circle, a perfect circle, and then the trace itself is of the surface we just measured it, and that's that. All right. Okay, so that looks acceptable based on the print and what we know about it. So I am going to say next on there, and it's telling me instructions to move to the next location, the datum point 2. So I'm going to come up just before it comes to the lip for the thicker section, and I'm going to put in the height at that location, which is 3.75. Enter that. Part name stays the same, but I can select a comment, which is datum point 2 ID middle. It's on ID, so I'll apply and again select the motor. There is a manual spin option on this, and that is if you have a part that's larger than the air bearing, the motor that's sized for this air bearing, you can still get the measurement you need. This is a 75 pound load capacity for the motor, but the system itself will take 125 pounds. So, roundness of that part is 1 thou even, and the TIR is 1 thou and 5/10. So I have satisfied with both of those. There's 2 plots on there, and what I can do is I can print that result, and that'll give me that trace, everything I see on there. And I put in the customer's logo, so that'll come out on the print. And instead of printing it, I'm actually going to save an electronic version of it. The information I put into part name and comment, as well as what type of measurement it was, reference axis in this case, are preloaded in the file name. So I'm just going to accept those and save it, and then exit out of the print preview and finish that. So now I am ready to take my concentricity measurement, because when I do select concentricity this time and say out of plane, and next it says that a reference axis is found and the day and a time that it was established. That's important to note, because later on when we move this part we have to reestablish the reference axis, and we can't use this. So it tells me to move to the surface that I want to measure. So I'm going to back the probe off a little bit and come up into the thicker wall section. In this case the print calls out for that ID to be concentric within 0.003. Doesn't say where on that ID, so I am making a decision. I'm going to measure 3 places, both ends and somewhere in the middle. And that's a decision the customer needs to make, and either define on the print where specifically they want it, or make some determination of some sort of averaging. So I need to enter in the height of this location, and I'm at 4.25. Enter that. The comment here is going to be thick wall section center. I'm still on the ID. I'll hit apply and use the motor. So I have a concentricity of this location of 2 thou 607, and that is within the tolerance. The tolerance on this print is 3 thou. Gives me in my results screen here all the information about reference point, datum point 1 and 2, and the reference axis. It's date and time stamped with the notes that I put in for comment and part name, as well as the concentricity of this surface to the datum, the roundness of this surface, as well as some other information. And I'm going to print that. Again, I'm not going to actually send it to the printer. I'm going to save it, and I can print it later. I can just save it electronically in my system. So I'm finished with that. Now what I'm going to do is take another concentricity measurement, but this time I'm going to come up about midway on that ID, and I am at 4 7/8. So I'm going to go to out of plane. And I'm going to just take the thick wall section. Instead of center, I'm going to say midpoint. Apply that and use the motor. It takes about 11 seconds for this to take a rotation, gather up all that information, put it into the algorithm, and display the results. So very quick. And So what I've got for concentricity here is 2 thou, 429. Again, it's acceptable, meets the tolerance. All the same information up here. So again, I'm going to print the results, as I'll be sending these to the customer later along with the video. Okay, so I'm finished with that. I'm going to take a concentricity measurement of the top just before it comes over the top there, and the ID still. And I'm going to enter the height, which in this case is 5 1/4. Enter that. Again, I'm going to save what I had in there before. So I'm going to, instead of saying midpoint, I'm going to say top. ID is already selected. Apply, use the meter. So you can see in very short order we have taken 6 measurements. We've taken 7 measurements. We've taken roundness and TIR of 2 surfaces on the OD just to align it. We've taken 2 datum surfaces and captured that for determining the reference axis, and then we've taken 3 concentricities of the ID to compare to that. And the concentricity here is 1 thou and 422. Again, meets the spec. I'm going to print that and save it, and we can move on to another surface. So I'm going to come off the part now, and what I'm going to do is there's another tolerance on the print that says the face surface has to be better than, I believe it's 5 thou, TIR to the center line, and we've established a reference axis center line. So I'm going to reorient my gauge head to do a face measurement, and I'm going to bring this over so I'm right on the top of that face. And again, with my alignment, I'm going to bring that up. And this time I'm going to select perpendicularity, which is how we determine the perpendicularity to that center line. And it tells me I already have a reference axis, and that is a good reference axis that I've used. So here I'm going to tell the radius. So instead of using the scale on the height, I'm using the scale on the horizontal side, and it's 1.5 inches radius. And I'm going to say that this is the thick wall face. And that's top or bottom, depending on where you are. So it is top. I'm going to apply and again use the motor. And we've got perpendicularity of that face to the center line of 8/10 94 millionths. Obviously well within the 5 thou. It's acceptable. Again, I am going to save that data, that result, and then move on to the next one. So now I need to go to the OD, which is also called out on the print, that there is a requirement for an OD concentricity to that same reference axis, the same datum, and therefore the reference axis we've established. So what I'm going to do is, again, it's not defined on the print where that measurement should be taken, where it needs to be concentric. So I'm assuming the whole surface has to be. So I'm going to come just to the top edge, and I'm going to take 3 measurements here. Top, bottom, and middle. I'm just going to confirm that I'm on scale. I am. So I'm going to go back to concentricity, and I'll have to enter in the location of this height, and I am at 5 1/4. Height, 5.25. Part name is still in there. I'm going to say that this is on the OD at top. I can change this diameter or location to OD and hit apply, and again use the motor. And we have concentricity of 1 thou and 2/10, so we have a 3 thou tolerance. That obviously passes. I'm going to print that, save electronically. Move on to the next surface, and I'm just going to slide down just about halfway so I get sort of a sampling here. Select concentricity, and again it's going to be out of plane, and I need to enter in the height, which is 3.75. Put in OD at middle. Apply, use the motor. As you've been seeing, there's really two screens and two navigation for the operator. There's the setup screen, which we just saw, and then it flashes to the results screen with a polar plot. You can also have a strip chart on there for linear, and there's harmonic analysis and chatter, so you can do some analysis of what the part is in manufacturing, what sort of machine frequencies you're getting. So the concentricity there is 0.3 to 297. So I will save that. And finish, and now I'm going to go down to the lower part of concentricity and just up from the edge. Concentricity here I'm going to be at 2.25. Enter, still on OD, and I'm going to change the comment here to be at the bottom. Apply that, use the motor. Maybe you've noticed, I don't know how well this is going to come out, but down here this use motor and manual spin are grayed out until you put in the information, the relative information, height or radius. It needs that information in a concentricity measurement or perpendicularity. And once you apply those settings, then you have those buttons that become active. So at the bottom we're 0.2 21 millionths concentric, again within the spec, and I'll save that. Okay, so I've done all three concentricities of the OD of one surface relative to the ID, all three locations on the inner upper part, which is the thick, and I've done the face. The last part that needs to be, the last tolerance that needs to be measured is the face of the other end. So in order to do that, I'm going to have to flip the part because I can't access that. So I'm going to take the part off, turn it around, the magnet engage, bring it on scale, center it, and then I can use my setup screen here to bring it on scale. Now I can, if I need to, make adjustments for alignment because I'm going to establish a new reference axis. So I'm going to clear the TIR and see what my alignment is. 2.5 thou. So I'm going to tweak that just a little bit, just because I want to. So I've improved that now to 1 thou and 67 millionths, 1 thou and 1/10. So that's good. Again, I'm at the focal point of the tilt and center. So now what I need to do is go to my datum surface, which is still on the ID, but it's now the upper part of the ID. So I have to turn my orientation of my probe. These are detents, there's no locks, it just pops into place at 90 degrees. I'm going to go down to just before the ridge to the thicker part. And I'm going to see when I make contact with the course, just dialing it in, and fine. Make sure I'm on scale. Okay, I'm going to select concentricity. Now this is where I said it's very important that we put in the we pay attention to the fact that it says the reference axis has been found. I can't use that because I've moved the part. So now I clear the reference axis. It moves me back to the reference axis position and tells me what to do. I'm going to enter the height for this location, 0.1, which is 3.5. Still, I'm going to keep the common spool name. That is now available for me to edit because I cleared out the reference axis. And I'm going to put in a comment that I'm on the middle section of datum. I'm going to make sure I'm on ID, select apply, and then I have the choice of motor and manual spin. So this is going to give me the roundness and TIR of the first surface. There is a spec called ovality, which we're making the assumption is roundness. Ovality may be even out of roundness, more appropriate. So this is round to 1,000 and 234. The TIR is 1,000 and 584, so you're not going to get much better alignment when you're that close to the roundness. So I'm going to go to the next surface, bring it up to as far as I can without going off of the edge, the top part of the datum, and I need to enter in that it is 5.125, and on the data ID, and I'm going to call that upper. Again, you can use these fields for whatever you want. It pre-populates in the file name when you're saving. Some customers will put in, they require that their operator put in their initials. You can put in part numbers as well as part names, descriptions, whatever works for you. That's something you can set up your own system and procedure. So at the second surface of the datum, I am round to 9/10 and 9 millionths, and TIR is 1,162. Again, both of those are displayed there. I'm going to print the reference axis, which gives me all of that information. And I'm going to finish that, and then I go back to the menu, which everything is available to me. So now what I want to do, because all I'm doing in this setup is taking the face measurement of that edge that was previously sitting down on top of the iris centering device. So this is going to be a perpendicularity measurement. And so I select perpendicularity, and I need to set that probe on there. And it's a very small surface, so you want to make sure your ball is right in the middle of it. Probe is right in the middle of it. I'm on scale, so I am going to say what the radius is now, because we're doing flatness, of about 1.5 inches. And I'm going to comment this as the thin wall base. And it's on the top. I'm going to apply, and I'm going to use the motor. Okay, and that's the surface. This is the reference circle. In this case, it's how the flatness compared to the perpendicularity, I mean. And so what I can do, that's perpendicular to 4/10 33 millionths. So I can print that, but before I do, I want to show you that I can go into the configuration screen in the back end here, and I can select strip chart, and I can select harmonics. So I'm going to apply those, and what it's going to do is going to take that information I already have. Polar plot's still there, but it's added a bar graph with the harmonics and told me what the dominant harmonic is, which is at 3. I can select any harmonic along here that I want, and it'll print that out. Now I can also edit out data, and so if I go to the edit data mode here, I have these cursors that I can say, I want to take this piece right here. Now maybe it was a blemish in the part, maybe it was a purpose low spot or flat, but it stayed on scale. So I can exclude that data, and it'll recalculate my perpendicularity in this case with everything but that information. And I can do that numerous times, as many times as I want, and then I can reset the data to go back to all the data being included. So I'm going to print that, and you see it prints the polar and the linear, and again I'm going to save it. And that covers all of the requirements on the print in a very easy setup, quick and easy. And I'm going to do in another short clip, I'm going to show you how to set this up without using this centering fixture, because the part is heavy enough to sit on there without this. This is just an aid to make that alignment quicker.